Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by SatSearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to the episode. I'm joined today by Thomas Sinn, CEO and founder of Deployables CubeD, or DcubeD for short. DcubeD is a German-based manufacturer of actuators and deployable structures for nanosats and smallsats, and as well as the wider commercial space industry. In today's episode, we're going to discuss some aspects of testing and qualification for deployables and other similar technologies. So, Thomas, welcome to the Space Industry Podcast today. And is there anything you'd like to add to that introduction?
Thank you, Hybel. There is nothing to add. You summarized it quite perfectly. I'm very happy to be with you today.
Right, well, let's get into this topic of testing and qualification. Now, deployables kind of need to work first time when they're used. They're often mission critical. Can you provide an overview to begin with, just of what sort of testing and qualification, what do they mean in the context of deployable systems?
Very good point, because you're right, deployables need to work the first time and they are often mission critical. And that's why a lot of companies or satellite builders go away from deployables because they are just afraid of them not working in space. But when we're looking into where the space industry is heading towards a new space constellation that need high performance computers on board, we just need to have bigger structures. And then we cannot go around the use of deployable structure because the satellites are standardized. We can pack them quite nicely for launch. And when we are in space, these deployables bigger. And this also means that the reliability and the checks that we can do here on the ground need to be improved. And this specifically means how can we prove that the deployable will work in the space. And we are trying to simulate all the conditions that are on the way to space and in space on these deployable structures. So we often do a test as you fly approach. So we start within the stored configuration where the deployable is then subjected to the launch vibration and also the shock that it will see during launch, normally on a shaker table. And then when we are up in space, we'll have thermal cycles that we get through the orbits. If we go to LEO, there is one orbit every 90 minutes. So we have to go through thermal cycling, preferably in a thermal vacuum chamber. And then most critically is the deployment that needs to work after all this launch and orbits. And here, ideally, we want to have it in zero gravity, but that's very hard to do here on the ground. So we need to figure out how can we do a gravity offloading system or maybe fly it on a parabolic flight or other methods to offload this gravity as much as possible. And the next thing is also, okay, as soon as it's deployed, how will be acting in a space environment? What will happen over the lifetime of this deployable? So there's a lot of testing and analysis being involved in increasing this reliability. And that's what we are also working here at DcubeD to still trying to improve on how we can make it more accessible and also a shorter time frame, and therefore also decreasing the cost for this testing while still increasing the reliability.
A lot of aspects that need to be really analysed deeply, and the nature of those analyses obviously relate to the missions that the deployable is going to be used on. So maybe just to give the audience a better understanding of that, I wondered if you could provide some examples of different mission scenarios in the context of new space, perhaps, where deployables are emerging as a key requirement.
Right now, we are developing a deployable solar array for new space nanosat constellation, but also it can be used for smallsats. And here, the idea is to enable 100 watts of deployed power while just fitting in a 1U cube satellite. The application for these are especially for communication missions where we need quite high power that we can then transmit more data. But there's also many applications where we go for electric propulsion as we need more power there. And then also, of course, as I said before, the computers that are on these small satellites are getting bigger and more advanced. So we need more power there. Most of the missions we are working on right now for our new space customers are actually in low Earth orbit, so between 400 and 500 kilometers. But we've been also tasked with some mission, not only for the deployables, but also more for the actuators going outside LEO, going to GTO, going to the moon, but also to the Lagrangian points. So there is always something that we need to keep in mind that, new space right now is mostly in LEO. There's more and more applications that are looking outside of LEO. And here we need to see what kind of requirements are more constraining the developments that are then outside LEO.
Quite a range there again. And obviously, as you've mentioned, testing's vital for such missions. And then the different standards and the different organizations you have to work with will dictate which sort of standards and qualification aspects that you need to adhere to. Now, there are various established Space Agency standards for testing, such as ECSS and GEVS, etc. Do you adopt these standards sort of straight away, or what other approaches do you take in using the existing standards for testing and qualification?
That's a good point. We started with ECSS and NASA GEVS to look or to get target where we want to go, but we realized quite early that if we would follow it completely as it's described here, we would develop a product that is much too heavy and it would be ridiculously expensive. So we are working together with NASA and ESA to figuring out, especially for new space application, how these standards that are developed for manned mission, for really these 1, 2 ton, 3 ton satellites that are flying to Mars and flying to GEO, can be adapted for a new space application. Because there are some things that are undiscussable, like the reliability proof of our actuators. Here we need to show that we have the reliability proven in ECSS to be even considered to fly on any kind of mission. When we are looking now on the deployable structure, where it's more advanced concept, then especially some of the ECSS design rules don't necessarily apply to them, because it would get just too complex and it would be a constraining factor. So here it's learning on both sides, on the new space companies like us, but also on the agency, ESA, European Commission, how these standards could be adapted to fit a more commercial goal. Because at the end, is if we are not flying humans, we are flying small satellites, then we can clearly discuss on the safety factors and all the necessary testing to make it a more viable product that we can also compete here in Europe.
When it comes to the use of the deployable systems and actuators that you develop, are there any specific challenges in the final assembly, integration and testing that need to be considered?
Yeah, there are quite some challenges, but with our experience that we have over the last decade now in deployables, we got quite good in tackling them. The deployable is a quite complex structure with often many mechanisms on there. If we look at our PowerCube solar array, it's a origami folded solar array that needs to fit in with the 1U box. So one of the biggest challenges is to manufacture it as much as possible in one piece. So to really reduce the assembly steps, then to fold it in a controlled manner into this deployment box, ensuring that we can always fold it the same way. So that's why we could also qualify it before, because we knew exactly how it was folded before, how we fold it every time when we build a flight model for it. Then we went through the test campaign. But then we also need to, of course, show that it's deploying properly with each of the products that we are delivering, because we need to show it on the ground that it deploys in space. And we are going here the approach for making it as simple as possible. So we say if the deployable deploys under ground load, so 1g of gravity, then it will deploy for sure in space. And then after this deployment test on ground, we need to pack it again, prepare it one last time for flight. So there's a quite long process involved with every deployable, but we are making good progress in making this very standardized. Because at the end, we want to enable commercially off-the-shelf mass products. And if we are every time spending months doing these deployment tests separately for each product, this is not feasible.
Right, excellent. So it's really about ensuring that reliability as efficiently as you can. And I think, some people in the industry may have different opinions and experience of deployable systems. And I'm sure in the discussions you have with prospective customers or current users, you come across some common misunderstandings or misconceptions. I wondered if you could just discuss a few of those, particularly when people are thinking about the decision making when it comes to the use of deployables or integrating them into a design.
That is a good question, because we also face these misunderstandings quite often when we talk to our customers that are in the nano smallsat world. When we say, we are developing deployables, they always say, we don't need deployables because they are too complex, too expensive, and they don't have high enough reliability. Because they think often of like these deployables that are developed at almost every university right now, which are more used for educational purposes. And then when you go a level higher, is when you think of these deployables that are on big satellites, the big solar arrays, the big antennas, there many people just see this huge price tag related with it. The thing that we are trying to do is to really deliver the trust back into deployables, that people see deployables as a reliable means to overcome launch vehicle constraints. Because if we really want to have a small form factor in a satellite that is possible with using commercially off-the-shelf electronics and computers, we also need to not limit ourselves to the small form factors, and we need these deployable structures in space. And as we want to produce them in mass production, there should be also a significant decrease in price and availability of these deployables, delivering more trust in the whole deployable concept. And we hope at one point we come to a conference and we say, we are working on deployables, and that then people don't say, it's too complex. We don't believe in the working of deployables anymore. That they say, this is the way to go. Put the deployable on our satellite.
That's obviously on the technology side from your point of view. Now, just as a final question, I wondered how you also saw the mission requirements evolving for deployables over the next 3 to 5 years. If you look beyond missions that are currently slated for launch, currently booked for launch, and what sort of capabilities deployables can provide missions, and where the needs for those missions are coming from the commercial sector.
So we see a clear need for deployables, especially in the area of power generation, so solar arrays, and then of course deployable radiators to get rid of all the heat that so much power can generate. Then on the other hand, it's clearly deployable antennas on the communication side, as well as on the Earth observation X-ray antennas. Here, we also need to have a bigger plane than that is possible with a satellite. And then there is ideas using the orbit sails and solar cells for propulsion and space debris removal. So there's quite some applications are in the pipeline for the coming years, especially for these nano and small sats. When we look at the requirements for any of these structures, we will probably see a change from especially the lifetime of these structures, because right now we are building them that they can last for 5 to 10 years. But if we really look at how many of these new space constellations are planning their business, we are not talking about a mission lifetime of 5 or 10 years, but more maybe 1 year or 1.5 years, or even shorter. The idea would be to reduce the price of the launch and also of the whole satellite, that it can be replaced more frequently with the newest technology. And with that, there is a lot of testing no longer required to really prove that it needs to survive these many years in space. And this would really greatly decrease the price, because at the end, the long time testing is what is driving the cost here of deployables, to make really sure that after the deployment, they stay in the configuration they should for the whole mission time plus X. So I think this will be one of the main changes in requirements. And this influence almost all the downflow into many other requirements. The only other thing, I would also think that more standardized interfaces would be great to have, to really make it possible to have commercially off-the-shelf products. Right now, we are offering most of our products with adaptable interfaces to fit many different satellite provider, rocket providers, guidelines. But I think also in the future, having them more standardized through the companies would greatly decrease the costs as well for deployables, for mechanism, and then for the whole satellite and the service as they are linked to each other.
Excellent. Well, thank you very much, Thomas. That's a great place to wrap up. And yeah, thank you for all the insights you've shared on testing and the use of deployable systems. I think this really taught the audience quite a lot about what goes into the preparation of such technologies and the uses of them in today's missions and tomorrow's missions, of course. It was really great to speak with you. Thank you.
Yes, thank you very much for the invite. I'm always happy to talk to you about the newest trends in space, and I'm already looking forward to our next talk.
Great, thanks. If you'd like to find out more about DCube's work and product portfolio, the links will be in the show notes, and you can also find out more on the satsearch.com platform. If you have any specific needs for product quotes, technical documentation, introductions to the business, or whatever else is required for your mission design, trade design, or procurement purposes, you're obviously more than welcome to use the free request system on the site too. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.